Well, welcome back to our practical problem solving clinic discussing experimentation techniques. This is part 3. In part 3, we're going to be talking about types of designed experiments that we introduced in part 2 and give you an introduction to the Taguchi designed experiments. So I'd like to introduce 5 different types of designed experiments. Single factor experiments, multiple factor experiments at 2 levels, multiple factor experiments at 3 levels, fractional factorial experiments, and the Taguchi orthogonal arrays. Single factor, multiple levels. These experiments are used to determine if a given process variable produces a statistically significant effect on some characteristic. So that's one factor. Although this one variable is used in this type of experiment, many levels of that variable can be studied simultaneously. An example of a single factor experiment is suppose that we want to know if our source for raw material plays an important part in determining the quality of our production. The variable supplier becomes the single factor in our experiment. If we use 4 different suppliers for the same material, then each supplier becomes a different level of our factor. 2-level multiple factors are used to study the effect of several factors, each run at 2 levels. N factors refers to the number of factors, in this case 2n. This type of experiment is capable of showing both the main effects and interactions among factors. It assumes a linear relationship between the factor and the response variable. Here's an example of a 2x2 factorial setup. You see across the top, factor A, level 1, level 2, factor B, level 1, level 2. That's a 2 to the 2 factorial setup. 3-level multiple factors are 3n's. They're used to discover the effect of several factors run at 3 levels. They're capable of showing both the main effects and interactions, but they also provide an extraction of linear and quadratic effects. So you see the graph on the right, you'll see the linear effect, which is assumed to be a line or a straight line and some slope, and the quadratic effect, which might mean that at some point, let's just say at level 1, it's on the upslope, but at level 3, it might be on the downslope. So a 3n factor is used to consider a quadratic effect in the results. Example of a 3x2 factorial setup: factor A, level 1, 2, and 3, factor B, level 1, 2, and 3. This is a full factorial experiment. So both the 2n and the 3n experimental designs are referred to as full factorial designs. This name means that the experiment crosses each level of each factor with each level of every other factor. Full factorials allow us to see every interaction that might take place between variables. Now, there are limitations for full factorial designs, and that is as the number of variables increase, the amount of data required also increases, and in a dramatic way. As a result, the time and cost required to operate this type of experiment can get very large quickly. In addition, you might consider that the benefit of studying all the higher order interactions is somewhat questionable. This chart explains the cost of full factorial experiments. In this case, a 2n. You see on the left-hand column the number of factors, 2, 3, 4, 5, 6, and 7, and the number of required trials that you'd have associated with each one of the factors. And if you want to repeat or replicate each one of those trials, you can see that with 7 factors on a 2n, and with one replication, you'd be talking about 256 different trials. Very expensive. Well, we have an alternative. Because full factorial designs become time-consuming and expensive to operate as the number of factors go up, experimenters have searched for alternatives to improve the efficiency of their tests. Sir Ronald Fisher developed fractional factorial experiments, which solve the problem. So instead of full factorial, we're talking now about fractional factorial experiments. Well, clearly, the benefits of fractional factorials is that we don't have to collect as much data. And fractional factorials provide adequate estimates of main effects with the least amount of testing. And concerned about interactions, while interactions may be buried within the main effects, fractional factorials are certainly a good option if interactions are thought not to exist or if they are of no interest. As we've mentioned, in full factorial experiments, every level of every factor is crossed with every level of all other factors. This allows us to see every conceivable form of interaction. In fractional factorial experiments, we focus on the main effects, and interactions are of a secondary consideration. Lower order interactions may have some meaning in manufacturing settings, but with proper planning, we can often eliminate them from our design by choosing our characteristics of interest very carefully. When you consider full factorial experiments, by the time we reach a 4th or 5th order interaction, it's usually very difficult to interpret an effect. In fractional factorial experiments, we focus on combinations that are needed to see main effects. All other combinations are of secondary consideration. In some circumstances, we can still study specific interactions in fractional designs, although we cannot study all interactions. Higher order interactions, for example, are not studied using this type of experiment. If you consider a 7-factor, 2-level full factorial experiment, that would require you to have 128 different setups. 2 replications means 256 trials. Please refer to that table in the lower right-hand quadrant. Full factorial 2-7 would give you lots of 3rd, 4th, and 5th order interactions. They may be meaningless, and it costs lots of time and money. If you consider the same experiment in a fractional design, the total number of trials, instead of 128, you'd only have to run 8. Replications are not usually performed, although they can be, and it is possible to study a limited number of interactions. Cheaper and faster fractional factorials allow you to do more studying. Although Sir Fisher introduced fractional factorials well over 50 years ago, they have only become popular recently, and that's because of the introduction of Taguchi fractional factorials. The popularity of this type of experiment is primarily based on the work of a Japanese engineer, and the technique is often referred to as the Taguchi method. So let's pause a minute and have a bit of a summary. Designed experiments exist to handle a wide variety of factor and level combinations. The classic design is called a full factorial experiment. Full factorials work well when the number of variables is small, but they get quite cumbersome when the number gets large. Enter Dr. Fisher, who developed fractional factorials that offer a good alternative if the analysis of all possible interactions is not of interest. Section 3.5, we're going to be talking more about the Taguchi designed experiments. The Taguchi method was conceived by Dr. Genichi Taguchi, who was working for the Japanese Electrical Communications Laboratory, ECL, following World War II. Think of them as the Japanese version of Bell Labs. Taguchi's purpose was to improve the efficiency of experimentation in research and development. Read that as they were trying to develop many new products, and they needed to experiment with hundreds and thousands of items, and they couldn't do it with the full factorial designs. Taguchi developed these techniques as an engineering approach. They were made popular in the United States by the American Supplier Institute and the Ford Motor Company in the mid-90s, when Ford introduced the American Supplier Institute and shared these methods with automotive suppliers. Taguchi developed a series of orthogonal arrays that systematically partition experimental variation into structured patterns. He developed a series of linear graphs that further demonstrate the structure to the experimenter. But most importantly, Taguchi developed a new philosophy of designed experiments. And that philosophy is that designed experiments should be an engineering tool to enhance productivity, not a mathematical model. This new philosophy speaks to the engineer or researcher's need for cost effectiveness and efficiency over mathematical rigor. The classical designed experiment contains some significant limitations and is more suited for the laboratory than in the industrial R&D or manufacturing setting. Taguchi's answer to limitations of designed experiments is that you should eliminate trials aimed at classifying interactions, especially higher order interactions, and test more variables, do more experiments, use simpler analysis to advance the cause of improving productivity and quality. To some degree, this is an argument of quantity over specific quality. Taguchi's experiments are characterized by their use of orthogonal arrays as a template for the design of experiment. Orthogonal arrays specify how many factors we can use, how many trials we should run, and where to set each factor for each trial. And to the right, you see a conventional Taguchi orthogonal, what we call an L8 array. In an L4 orthogonal array, 4 trials or experimental setups are performed to study 3 factors. You can see on the little table to the left, 1 indicates for the low level and 2 indicates for the high level. So we have in the L4, 3 factors using 4 trials. And compare that to the full factorial, 3 factors would require 8 trials. So the L4 immediately cuts out 50% of the number of required trials. Much more efficient. Now take, for an example, the next step up, the L8. Now the L8 provides for as many as 7 factors at 2 levels. And that's done with 8 trials. Compare that to the full factorial requirement of 128 trials. 8 trials versus 128. So now I think you can see that fractional factorials, in terms of efficiency and speed and cost, far superior to the full factorial design. When assigning factors to orthogonal arrays, if we do wish to track a possible interaction between two factors, we use something called a linear graph to tell us where and in what column the interaction will fall. Linear graphs are visual aids that help in assigning the experimental values to columns of the orthogonal array in such a way that we can see a specific interaction. So the L8 orthogonal array has two possible linear graph combinations. These linear graphs show interactions between columns on the L8 orthogonal array. The interactions between factors occupying the numbers at the vertices will show up in the columns represented by the numbers between. We'll show you that in a moment. If only 4 factors are needed for the experiment, there are 3 columns remaining in the L8 array to track interactions. If, for example, the 4 factors would be assigned as follows: factor A in column 1, factor B in column 2, factor C in column 4, and factor D in column 7. Go to the next slide. Then the interaction between A and C, AC would fall in column 5. The interaction between AB would be found in column 3, and the interaction between BC would be found in column 6. So although Taguchi fractional factorial experiments come in all shapes and sizes, the basic method is the same for any design. And the experiment can be simplified to a few basic steps that apply to any of the designs. As we had with hypothesis testing, conducting a Taguchi fractional factorial experiment has 8 basic steps. First, and arguably the most important, is to plan the experiment. Second, to select the orthogonal array that best fits the plan. Third is to select a linear graph that allows the best assignment of the factors to the orthogonal array. Step 4 is to assign the factors to the columns in the array. Step 5 is to run the experiment. Step 6 is to analyze the experiment. Step 7 is to draw the appropriate conclusions from the analysis and optimize the factors. And step 8 is to verify the result by performing a confirming run. So let's proceed with step 1A. Use the team approach. We've mentioned this several times already, that you need to collect the people who are most closely aligned with the process. Production operators, production supervisors, quality technicians, quality engineers, and engineers, maintenance people who understand the process and see the work every day. Ask the team to carefully define the problem specifically and carefully. If it is already defined, review with the team. And use all the tools that you can, like brainstorming, Pareto analysis, and even is not. In step 1B, we want to select the output variables. Decide which characteristic we're going to measure. Choose a characteristic that is evaluated with variables data rather than by attribute measures, because variables data provide more information with fewer samples. Looking at historical information, assure that the distribution of the variables data approximate the normal distribution. Determine how to measure the characteristic. Assure that the accuracy, repeatability, and reproducibility of the gauging system is within range. And assure that those that are going to select and measure the samples are proficient with the gauge use. We're going to select the experimental variables. Assure that your designed experiment team includes people who are knowledgeable in the process, the problem, and the analytical methods. Create a list of potential variables that can be made through brainstorming techniques. The top candidates for the experimental variables can be selected through Pareto analysis or group selection techniques. So now we're going to select the experimental levels. Consider the use of only 2 levels, as this keeps the number of required trials at a minimum. This is recommended unless there is a specific reason to do otherwise. 2 strategies. First is to maximize the range between the levels without knowingly creating defects. So we want to select the levels that are high and low and not close together. They want to be as high as maybe that you've ever run or can imagine in running, and low as you might imagine on running. You don't want these things to be the factors to be close, because then clearly you're not going to show if there is a difference. And strategy 2 is to duplicate the range which occurs in real life, and that in production, if it is known. In step 1E, we're talking about controlling noise, and that is not audio noise. We're talking about extraneous and unusual variation. And to do that, we may use complete randomization of experimental trials and of replications. Method 2 is to hold all the variables constant to the greatest degree possible. This is not as effective as randomization because it's very, very hard to hold all variables constant all the time. Step 1F is to decide on a method of analysis. Determine if replications or repetitions are going to be done. Or will we just have one sample per trial? So a replication is repeating the trials in some random order. It's effective but difficult to do. And repetition is taking more than one sample per trial while we have a given setup in place. Most times, repetitions are favored over replications. In step 1F, we're going to decide on the method of analysis. With your team, review the steps in the analysis before you start to assure that your experiment will meet your objectives. Determine what form the data will be in to allow proper analysis. So just don't scribble it down on a piece of lined paper. Create a form so that the data is accurately recorded. Then we're going to determine the level of error that is going to be tolerable. Choose the F statistic. Determine the alpha level and the acceptable level of tolerance. As we've seen in many of the experiments I've talked to you about in this session, 5% is typical. 1G, then we're going to plan and collect the data. So we have to decide who will collect the data, when will it be collected, how will the samples be taken, where will the samples be taken, and create any forms if needed to record the data. Now this may sound to be unnecessarily detailed, but we want to make sure that no extraneous information gets recorded in the data, nothing strange occurs, nothing unusual. We want to make sure that we're faithful to the experiment. Step 2 is to select the orthogonal array. So in your team's thinking, they have to consider how many factors do they want to include. Remember, each factor occupies one column in the orthogonal array. They have to consider if there are any interactions, and bear in mind each interaction occupies a column on the orthogonal array. And do we wish to test at 2 levels or 3? Again, 2 levels are easier unless there's a really good reason to have 3. Now, you can find orthogonal arrays in different books, or there are a couple of websites that I have listed there for you to find them on your own. Steps 3 and 4. In this step 3, we're going to be selecting the best linear graph. If interactions are going to be studies, consider what factors a team think may interact, and determine if there are factors that might interact with more than one factor. If so, pick a linear graph that allows the analysis of these factors. If no interactions are present, linear graphs are really not necessary. In step 4, we're going to assign the factors to the orthogonal array using the linear graph. Assign the factors to the orthogonal array. Now, some factors are harder to change from level to level than others. The setups are longer, or maybe the materials are harder to change over, or cost just more to change factors from one trial to another. The assignment of these factors to the array should take this into consideration. When you take a look, for example, at the L8 design, you'll want to assign these hard to change factors or expensive to change factors to the first and third columns. Step 5 and 6. In step 5, we're actually going to run the experiment and make every attempt to avoid disrupting production. Good experiments should not create excessive scrap. However, sometimes it is unavoidable to achieve understanding. Attempt to duplicate production conditions as much as possible. In step 6, we're actually going to analyze the experiment, review the data for signs of abnormal variation or measurement error. Taguchi experiments, like all DOEs, are analyzed using the analysis of variance. We're going to perform the analysis as planned before the data is collected. Don't perform analysis to fit the numbers. Since we'll be performing calculations by hand, check your figures before presenting the results. Step 7, formalize the conclusions using the criteria established before the experiment was run, and we'll determine if any significant effects are present in the data. If several effects are present, determine the relative size of the effects. We'll also determine which level of the variables produced the most beneficial effect. Publish results formally before proceeding. And step 8, we're going to verify the results. Set the process at the best level suggested by the experiments. Note that only the factors that produce a significant effect should be changed. Sample the process and measure the quality characteristic in question. If the results are confirmed, make plans to permanently change the process. If the results are not in line with the original study, find out why and redo the experiment. Following your verification step, you may find that the results may not be reproducible. Here are some hints on perhaps why and remedies. In the first case, a factor or variable not included in the experiment somehow changed during the data collection and produced an effect that was not tracked. In the future, you can randomize all trials if this was not done previously, but more likely you'll have to put better controls on non-participating variables. Clearly, in this case, a variable that was important to the process was not included in the experiment, and the next time in your next set of validation experiments, you'll need to include that suspect factor in the experiment. Or perhaps there were interactions that existed and were mixed up with the main effects. You didn't know that there was going to be an interaction, but one existed. So as a remedy, review the assignment of the factors to the orthogonal array. Were any of these interactions overlaid over the main effects? Can they be moved to a different column and separate them? If all the columns are occupied, use a bigger layout to account for more interactions. If the process was not stable during the experiment, an assignable cause of variation exists in one of the factors. Clearly, as we mentioned earlier, before you start your experiment, the process needs to be stable. So a remedy for this is to plot the data on a control chart and look for trends or runs that are not explained by planned changes in the experimental factors. Record all the ambient conditions during the experiment. Record all the possible extraneous controls that might be out there so that you can get a hint on what's going on. Or finally, an error may have occurred in the calculations. So we need you to review the reference material to see that the correct methods are being used. Make sure you understand the material. Have someone new check the calculations, and if the analysis was done by hand, try using computer software. And if you're using computer software, make sure that the data was recorded faithfully. So a little summary here of basics of the Taguchi experiments. Genichi Taguchi's methods are meant to be an aid to engineers, not intended to be mathematical models. Taguchi's fractional factorial designs greatly improve the efficiency of experimentation. They are fast and relatively inexpensive to perform. Although many different designs exist, all are conducted in a similar manner. And regardless of the design, the basic steps in the experiment are the same. So I'd like to thank you for participating in part 3 of our practical problem solving clinic, focusing on experimental techniques, and invite you to proceed to part 4. And again, credits to the Greater Detroit section of the American Society for Quality for an introduction to hypothesis testing, and to the Ford Motor Company and their work with the American Supplier Institute, Genichi Taguchi and Yuan Wu's offline quality control, and to Mr. Tom Dole, a colleague of mine, for his enduring work in training and continuous improvement. Thank you.